So I'm Balajiraja Ravinarayan, Tessent Application Support Engineering Manager for Europe. So I'm going to be co-presenting this with Kevin. Unfortunately, he's not here. He's from NAX Group and Intel Corporation. Okay.
That's fine. Yeah. Like, that's fine. Then can you?
Okay.
Yeah. I'll be the first one.
Okay. Right. Okay.
That's it. Pretty fast.
Yeah. Okay. Here is a brief agenda of what we are going to discuss. The purpose of this presentation is to delve into the diagnosis methodology and also outline preparations necessary to enable smooth diagnosis flow. Subsequently, we'll also be discussing about integrating layout-aware feature into the existing diagnosis workflow, followed by looking at the results we have obtained and also outline subsequent steps that are required to be taken once we have this flow enabled. Which, right? Okay, here's the overview of the system. Right, the device of interest here features both multi-core and multi-partition configurations, which are almost a standard in most SoC designs now. SSN and EDT are utilized for logic test purposes here. Let's briefly discuss about SSN concept for a quick refresher. So SSN data path is a synchronous n-bit wide bus used to stream scan test data. The primary access to the SSN data path is through SSN in and SSN out, and with SSN clock as a synchronous source. The SSH node, which is the orange rectangular box here, transfers the data between the SSN data path to the EDT channels or to the scan chains directly. The SSN data path traverses the design hierarchy, delivering scan data to any number of active SSN nodes in the design. By the way, all the SSN nodes are configured or set up via IGATAC, which remains static per pattern in most cases. Okay, getting into the diagnosis methodology now. So the initial phase of diagnosis begin with encountering a failure, which although undesirable is crucial. However, the paramount focus here lies on root causing, what's the reasoning behind the failure, right? So the log file obtained from the ATE should include this information. You should need your failing pattern name, failing pin name, failing cycle information, and then expected data when the failure occurred, and then actual data when the failure occurred. So with this information, we can move to the diagnosis flow. Here is a sample screenshot from V90K tester. In most cases, right, I mean, the log file obtained from ATE can be directly utilized in Tessent to facilitate diagnosis. In some cases, there may be minor modifications required to the log file obtained from the ATE. For example, here you can see the expected and the real data is ones and zeros, but Tessent would like to have them as highs and lows, minor modification. But in Intel scenario, where we need to do a bit more alignment to get it working in the Tessent, the reason for that is Intel runs a preamble sequence in a form of a reset sequence prior to the actual actual scan data itself. So what that means is that reset sequence is not programmed via Tessent. So Tessent has no memory of what happens during that reset sequence execution. However, the log file obtained from the ATE has this preamble sequence appended. So we need to find a way to synchronize or offset the cycling numbers to ensure Tessent understands it, or else you're not supplying a valid data to Tessent to produce diagnosis results. So this is a tripping point that Kevin and team wanted to highlight. With the log file in hand now, we can directly move to the Tessent. Right now, we have a bit more descriptive here. So in the Tessent shell, now the ultimate goal is to remap the failure that we have obtained at the top level of your design to the core level to perform effective diagnosis. So in the Tessent shell, the context is set to failure mapping. And then the second step is you're reading your top level description. Third step is you're going to run the check design rules. The check design rule ensures the design DRCs are okay. It flattens the design and also learning from the design. Okay, what sort of a model I have got. And then you're reading the pattern that failed, and you're going to supply the log file produced from the ATE into the Tessent. And at the end of this stage, you're going to write out issuing the command write failures, write out the failure file, which is mapped to the core level now. So now with the file mapped to the core level, we can move to the scan diagnosis phase. This Tessent shell is set to the context scan diagnosis now. You're going to read the core level flat model, pattern at the core level, and then supply the remapped failure file generated from the previous stage. And ultimate goal of this stage is to issue this command diagnose failure, which is going to produce a diagnosis report, which includes your possible suspects and symptoms, right? Okay, this is one of the invaluable tip that we have employed as part of the diagnosis flow. So the way it works is, as I said, usually diagnosis begins only when the actual silicon failure occurs, right? So by deploying this create open socket failure, you can pre-emulate this behavior in the pre-silicon. So what it means is you can create this, issue this command in Tessent, create the log file, and then create the setup ready for diagnosis flow. It shows readiness, and also it prepares you for potential diagnosis flow. So this saves quite a lot of time. And one of the tip here is, obviously when you issue this command, Tessent produces a huge log file with each and every cycle failure. The purpose is to validate the flow. So you can cut down on the cycle numbers here and then just use few numbers to validate this flow. This helps quite a lot. So going into the layout aware diagnosis now. So one of the information that we need to transmit to the Tessent is the layout information. That is what is missing now. So it's as simple as that. So we have to give to Tessent the def and left files of your design. What the Tessent does is taking in left and def, and it creates an intermediate database called LDB. So layer database creation is a process where Tessent try and understands your def and left files, try and then do some layout verification in terms of like what sort of layers you've got, and any other macro information you've got. So it understands and maps it to the design that you've got. If the layout verification is successful, then you can create the LDB file and then proceed with the flow. But if it is not passing, it does have quite a lot of restrictive checks to make sure that it passes. If it is not passing, then you need to take few iterations to get it right. Okay, as I said, for the layout aware diagnosis, the collaterals, additional collaterals on top of what we've discussed previously in the diagnosis flow is your core level left files, top level left files. Tech files here means your memories or custom macros or standard cells. Def file of your core and top is provided to the tool. And these are industry standard formats. You get it the standard from any tools. Now, with this information, I'm just going to talk about how to create the layout. So context is still scan diagnosis. You're going to read your flat model and then supplying this left and def files. Create layout will create the layout database. And the next step is the layout database that you've created. You're going to open that layout, proceed with read patterns that failed, and then remap failure log file, and then perform effective diagnosis here. You can do this in a single step. Just for readability purposes, we have split it into 2 steps. Okay, common pitfalls. These are important ones, very, very specific to Intel. Some of them are common as well. So when you generate the left files from request left files from structural design or physical design team, ensure that you have layer information covered as part of your left files. Without that, your layer verification is going to fail, and we had few iterations because of that. The other thing would be if you have a hierarchical course there where you wanted to perform hierarchical diagnosis, ensure to write out your def files with component information. So without component information, you cannot do the layout aware diagnosis at the core level. The second one is something that I've touched, where we need to find a way to offset or synchronize your AT log files to Tessent cycle numbers. If you're not providing that correctly, then we would end up having problem in generating the diagnosis, right? So reset sequence is one. The second one is this the compression of your scan vectors. If you're using X2 or X4, we need to ensure that we need to find a way to synchronize as well. And any other manually inserted delays must be accounted for as well. So without that, we would not have potentially a proper diagnosis report. And then we had some issues with that. So that's the reason we want to highlight that. This is another one, the TCD signature file. The Tessent produces this TCD file per retargeting mode. But in Intel's scenario where the product development engineering who are working only with the style files, they just archive the style files for production vectors. So what that means is they don't regenerate. I don't want to regenerate a TCD file. So what they do is, as an intermediate methodology, is to swap the signatures at the style file to the TCD file. They maintain only one. not the recommended way, but this is what they are doing. I mean, we've been trying to change, but this is one of the common pitfall as well. Okay, so concluding this one, right? I mean, the scan diagnosis is going to improve your diagnosis resolution. Obviously, with the layout information, you're going to gain X and Y coordinates of what the failure is. But beyond that, what Tessent diagnosis does is, I mean, the consistency checks between your layout and the data that you have in the Tessent for the pattern generation purposes. You can perform chain diagnosis, you can perform logic diagnosis. With the diagnosis report generated out of it, you can do the logical viewing and the defect classification, and then optionally, you can create the marker file for the physical view of the defects itself. So there are two important aspects of diagnosis flow with layout aware. One is dramatically reduces your suspect area. So based on the results that we have obtained, there is an 85% of false bridge suspects have been removed compared to non-layout diagnosis, which is significant for failure analysis team who performs this destructive fault isolation and stuff like that, okay? And then there is a proved 70% reduction in the open net segment as well, based on the results we obtained. And the second one is the diagnosis adds valuable classification to your diagnosis. I mean, for statistical analysis purposes. What I mean by that is doesn't just flag, hey, there is a potential bridge fault. It goes beyond and then says, hey, it understands whether the bridge is occurring between your corner to corner, intra-layer, or side to side, which is really valuable when you're doing fault isolation. Obviously, it reports X and Y coordinates. So validation in results. So this is the silicon results that we have got. So we have seen failures in multiple cores and multiple dies. And then we had failures and we have seen speed and stuck-at failures. And all this data are collected from wafer level test fits off the shelf, hot on the it's ongoing process as we speak. So this is the sample report that we have obtained. So what we are trying to highlight here is the boxes here highlights the diagnosis report with layout here. So layout status, and then layout of the suspect, and then layer on which it is failing, and then critical area of the suspects. So in comparison, right, the suspect reduction, you can see yourself, see for yourself, it was 199 before. It's one sample die that we are taking to 32, and then the symptom reduced from 26 to 15, which is significant in terms of gathering more information. So what we are trying to do in terms of, okay, let me finish this one. So how to read this report is the layout aware diagnosis report would look like this. With this report, you can get your logic location of the failure, and then we can classify what kind of defect that we have got, and then the physical location of the failure can be obtained as well. In terms of next steps, so as a next step, we are going to do root cause deconvolution. So basically, we are going to gather more data log. So root cause deconvolution is the process of differentiating possible failures in a population of failing devices from diagnosis ambiguity in a high volume scan diagnosis environment. So using all those reports, we can perform a parity analysis. I was glad to see from Mike Yellow's presentation, he was highlighting that this today. So we have in the background who does this. And then the next one is getting into the chain diagnosis. So it is slightly different to the regular capture pattern, because chain diagnosis is a two-step process where the first step would be to identifying the chain that fails, and then going back into the next step would be identifying the cell that fails. So that's it. That's all slides I've got. Unfortunately, Kevin couldn't join, but I will try and answer your questions if you have any.